we start. Hello, everyone. I'm Maura Pintor, and I'm an assistant professor at the University of Cagliari in Italy. And I'm happy to welcome you today to a new event for our machine learning security series. Today we have as a guest Giovanni Cherubin. Right before we start, I would like to share some information about the seminars. First, the event is live streamed and recorded, and you can find the recording in our website that we will post in the chat soon, and also on YouTube, where we host all our videos together with a course that we held at the University of Cagliari about machine learning security. So if you want to strengthen your background or know more about some specific topics, you can find everything there. I'd like to thank all the people who helped me organize this series. And now I give the stage to Luca, who will introduce the speaker for today.
So, hello everybody. Great pleasure to be here and also to introduce the next speaker of this seminar series. So, Giovanni Cherubin is a senior researcher at Microsoft in Cambridge, working with the Microsoft Response Center. And before joining Microsoft, he held research position at the Alan Turing Institute at EPFL, and he obtained a PhD in machine learning and cybersecurity from the Royal Holloway University of London. His research focuses on privacy and security properties of machine learning models and on the theoretical and empirical study of their information leakage. He also works on reliable machine learning tools, such as a distribution-free uncertainty estimation for machine learning, like conformal prediction. Some of his work on security and machine learning had also been recognized with the Best Student Paper Awards at SLDS 15 and PET 17, Distinguished Paper at USENIX 2022, and the USENIX Internet Defense Prize in the same year. So it's a great pleasure to have you here, Giovanni. The stage is all yours. And you're
Thank you.
Okay.
Not anymore. Hello. Thank you. Thanks a lot, Maura and Luca, both for the very kind introduction and indeed for inviting me here. It's great to be part of this series. So my plan for today is to give a sort of high-level, broad overview of what I believe to be the main topics within privacy-preserving machine learning, or PPML for short. I will also discuss a little bit about our research, but really the main goal will be to present the main attacks against machine learning in the context of privacy, and to give you also some ideas about defending against these attacks. So before we get started, let me start with a sort of motivational example, which I think reflects quite well the things I'm going to talk about. So this happened in 2020. Nicola Carlini from Google Research took GPT-2 at the time. I'm sure everyone is familiar with the GPT family by now. And well, what he did was he observed that by feeding the model some particular prompts, the model would spit out private information such as phone numbers, email addresses, and so on. Now, of course, as you're all aware, GPT-2 had been trained just on public data. So you could think of the data that the model was spitting out as not being very private, right? It was already in the public domain. But if you wish, this raised awareness on the fact that machine learning models do memorize their training data, and they might even leak this data. And this really brings us to the first kind of terminology, very important terminology thing that I need to say, and that is, by privacy here, I mean information leakage. I found this to be particularly important when dealing with security experts. For some people, privacy has to do with laws, GDPR, the AI Act, and so on. But for me, for this particular talk, privacy is a sort of security property, and it has to do with the information that a model learns or could spit out to an attacker. So cool. So let's get us started with some kind of basic scenario. Suppose we were to train a machine learning model based on some training data, and we were to deploy it on some, with API access available to users. So in this case, you see, sorry, I'm going to reduce the Zoom screen here. So in this case, you see that the model can get an image as input. And what it does is it predicts how many people are in the image. Simple. Now, as I mentioned, machine learning models, when they are trained, they actually memorize part of the training data. And so in this case, we have images. Some of the images might get memorized a bit more or a bit less. But the point is that when we consider an attacker who has access to the model, well, it might be possible for them to actually reconstruct some of the images or data records more in general. Cool. So my goals for this talk, as I said, I want to give you a high-level idea of the main attacks that one worries about when deploying a machine learning model. And all these worries have to do with information leakage. Then we'll go and kind of discuss a little bit, well, how do we protect against these attacks? And it turns out we do have very nice solutions, but we will see there's always going to be a sort of utility privacy trade-off in there. And there's a lot of subtleties to consider. And then finally, I am going to mention a bit of our work on this area. I forgot to mention, please do feel free to, to write in the chat. I'm sure Luca will be able to relay rather your questions, and I'm happy to answer them during the talk. Cool. So what does it mean for a machine learning model to leak? So this is kind of the setup we've seen, and this will be fixed throughout the presentation. So we have an attacker who has API access to the model itself. Now, let's further assume that this model now returns two things. It returns its prediction, or its labeled prediction, if you wish, and that is the number of people that appear in a certain image. And secondly, it also associates its prediction with a confidence value. And this confidence value tells the user how confident the model is about its own prediction, essentially. So now consider the following. So we have this attacker who has black box access to this model in the setup. And then additionally, which you can see in the bottom, the attacker has access to a set of images. And some of these images might have been used for training the model. Some of them might have not been. It doesn't really matter how the attacker gets hold of this set of images. And now I claim that this attacker might be able to figure out which of these images were actually used for training the model just by exploiting the attacker's access to the API. So these attacks are called membership inference attacks. They were introduced back in 2017. So I think, well, these are the attacks that have been the most studied throughout the PPML literature. And I think they're also the ones that give you a very good idea of what it means for a model to leak. So let me give you an intuition as to why such an attack might work. So the attacker has API access to the model, as we said, and they can take a look at the confidence score of the model itself. Now, when we train machine learning models, what we do is we minimize some loss function so that on the basis of the training set. So the idea is that for each of the training records, we would like the performance of the model to be good. Now, if we do follow exactly this sort of pattern, then you may realize that the model tends to be overly confident when making predictions about things, data records it has seen already in the training data. So, for example, here, this particular image did appear within the training set. And we can see there's a big spike in the model's confidence score. So, well, very intuitively, the attacker can just query the model and probe this. And then what happens when they input an image that was not used for training, where the model has never seen this image, so it might as well show a much, let's say, smoother kind of distribution of the confidence scores. And it may be surprising, but this very simple technique can actually can be leveraged to achieve a rather good membership inference attack. So how? Well, as I said, the attacker just need to produce the confidence scores and possibly set a threshold and say if the model is more than expresses more than a certain confidence, then we should then we should call the data point to be a member of the training set, otherwise not. Very simple, yet quite effective. So we run in 2022, a couple of years ago, we run a competition for evaluating sorts of membership inference attacks. So what we did was we picked several data sets and then trained various models and asked participants to kind of to break them in some sense, to figure out the membership for a set of data records that we provided them. So how did they do? So what you're seeing here is the attacker's success rate. So for membership inference across several tasks. So we had SST2, that's a text sort of language data set. Then we had CIFAR10 for images, and we had purchase 100, which is just tabular data, and it's commonly used in membership inference kind of scenarios. And well, the baseline, we ensured it would be 50%. And you can see that, well, they did manage to sort of break the attacks, to break the models in a non-negligible fashion. The very best accuracy is 60%, so not too bad. And mind you, this does represent, at least at the time, the state of the art of the attacks. Could there be better attacks? Well, possibly, probably. I mean, there's many new coming, but this was the status at the time. Now, this sort of this graph helps me introduce a second thing, which we'll discuss later on. And it is, we also evaluated some defense strategy against the attacks. This defense strategy is called differential privacy. I'll explain it later, but the idea is that we get this parameter epsilon, which you can see here on the x-axis. And the higher it is, the less private or the more leakage we allow there to be, and the other way around. So epsilon equals to 4 should be a relatively good sort of protection. Epsilon equal to infinity means we have no protection at all. And you can definitely see this sort of trend of attacks getting better according to this parameter. Now, something very important, and this is a sort of constant, if you wish, in privacy-preserving machine learning research, is that there is going to be some trade-off we need to make. Perfect privacy, at least for this sort of attacks, is not really something we can hope for. And the reason is that if you wish an intuition, is that for the model to be private, it shouldn't leak anything. It should not memorize anything. But on the other hand, we do want the model to memorize the concepts, right? So that's we always have this sort of trade-off to balance. And indeed, even in this case, numbers are not shown here, but I can promise you that if we were to increase this epsilon, meaning very, very low privacy, we would get much more accurate machine learning models, which are, of course, less private. Cool. So this is for membership inference. Now, I wanted to open a sort of parenthesis. This is kind of, if you wish, an advanced topic, which is very dear to me, and it is what metric do we use for evaluating attacks? And of course, this is quite important, because at the end of the day, if you want to decide whether you should deploy your model or not, really depends on which metric you choose, and what numbers do you get, right? So you really want to make sure that the metric is correct. Otherwise, you may end up with some privacy incident. So well, this was the scenario. So let's just think about membership inference, where the attacker has to guess the membership from a set of data records. And then the first idea that might come to mind is, well, let's just use the accuracy of the attacker, or the success rate. How many times out of n, how many times does the attacker get correct? This is a very good and intuitive metric. If I can tell you 60% probability of success, you know exactly what I mean. However, there is a little caveat, which can be quite important in some cases, and that is what is exactly your baseline, or rather, what is the baseline of the attacker? So let me show you the example here. Let's say that our training set is taken, this is usually the case, from the whole set of data that appears in the world. This is beautiful. Now, if I asked you to give me a very, very good membership inference attack, you don't even need to look at any model whatsoever. What you can do is just whatever data record I give you, just predict that it was not used for training the model, right? I mean, it is quite realistic to think that the model was not trained on a massive amount of data, depending on the model, of course. But this strategy would be extremely successful. So, but then you see that the success rate becomes a kind of useless metric in this context. So what we end up doing is relating the attacker's success rate to a sort of baseline. And a very nice way, I think, for doing this is the following. You consider an attacker who does have access to the model and carries out their attack. And then you consider an attacker who has access only to prior information. So say the prior probability that some data record picked at random happens to be a member. And then simply you relate the two of them, either by subtracting or dividing or so on. So this is kind of a common pattern used for generating metrics that actually are more meaningful than the attacker's success rate itself. I'm omitting a few details here, but hopefully this gives a good broad idea, and we'll be using this advantage notion later on. So I thought I'd introduce it here. Right. So let's get back to looking at attacks against machine learning models, privacy attacks, that is. We looked at membership inference. The next one is called attribute inference. You might already be able to infer, pardon the pun, what this is about. So the attack is as follows. The attacker is given a data record belonging to the true training set, right? Although they're not given all of the attributes or features of that record. So, for example, the attacker might be given the age and sex and other information about a user, but they might not be revealed whether they have cancer or not. So there is a particularly sensitive attribute that we care about. It could be one or more than one attributes, of course. Now, the goal of the attacker is, by exploiting access to the model, is to figure out the value or to predict the value of this attribute. So how do they do that? Well, you may be not too surprised to learn that the attack is quite similar to the membership inference idea I gave you before. So something we could do is we can, as attackers, we can iteratively replace the values of the missing attributes with all the possible completions, right? Of course, this is the trivial way of running the attack. And then we get back the score. And based on the score, so here we say cancer equal to no, and then cancer equal to yes. And using the confidence score of the model, once again, we can figure out whether what's the value, or get a good estimate of the value of the attribute itself. So yeah, attribute inference. I tend to find that whereas membership inference is extremely important, particularly for from a theoretical perspective. It's really a founding pillar, if you wish, of PPML. Attribute inference does tend to be favored as a sort of explanation for leakage in machine learning. It is something quite tangible, right? Someone is going to be able to learn more information about yourself just by using the model. And so this is a sort of warning note. If you're interested in pursuing PPML research, that attribute inference really needs a good baseline. So consider this example. We have a sort of similar data set before, but now we're one of the attributes is the occupation of a person, and the target data record that the attacker is given is that of an old lady of 86 years old. Now, even without having any access to the model, an attacker who were to predict retired as occupation, well, they would have probably a very high success, right? So, but by carrying out that attack, they would just be exploiting prior information about that target record. Now, this is exactly the reason why I mentioned the need for metrics such as the advantage, because we need to take into account the success of an attacker before and after releasing the model. If the attacker is already able to carry out the attack but before seeing the model, then that's not really a risk, is it? Cool. So we saw membership inference, attribute inference. Now, reconstruction attacks are, if you wish, a special case of attribute inference where what the attacker wants to do is to reconstruct the whole of a data record. So how do they work? Well, we have, again, the same setting as I promised, as before. But now the attacker has some particular target record that they would like to reconstruct, and so they do. So how can this happen? Well, I'll give you one example based on some work I did recently with Borja Balle and Jamie Hayes, both from DeepMind. So for this attack, we made very, very strong assumptions that favored the attacker immensely. And we call this an informed adversary, just because of all they know. So in this attack, the attacker has access to the model and confidence score. They even have white box attack, although that's not really necessary. And finally, and very importantly, the attacker knows the whole training set except for one data point. And that data point is what they want to reconstruct. Now, there's various reasons why it made sense to make this sort of assumption. If you wish, and one of the reasons is that if you can protect against this very, very strong attacker, then you can protect against much, much weaker attackers. And so you should be happy and able to deploy your models. So let me give you an idea of how our attack worked. Well, as I said, the attacker. By the way, can you see my mouse, my pointer?
Yes.
Kinda.
Yes.
Yeah. Okay.
Kind of. Yeah. All right. Cool. Yeah. Just a bit easier. Thank you. Thank you for confirming. So. Right. So, as I said, the attacker has access to the model, which was trained on the full data, and they have access to all the training data minus 1 point. And so the idea, well, our idea was, how about we create some mapping between the neural network itself and the image to reconstruct? And what a better way to create a mapping than to simply train a neural network for doing this job. And that's quite literally what we ended up doing. We trained a neural network which would take as input the target neural network to output the reconstructed image. Now, just to kind of very briefly, these were some of the results we saw for this attack. So on the top side, you see the original kind of target images. These are taken from the CIFAR-10 datasets, and bottom line shows the reconstructed ones. So yeah, we can achieve a pretty good reconstruction. Now, I think the main contribution, or a very important contribution, if you wish, of this work was the evaluation of potential defenses. So I promised we'll take a look at defenses later on, well, very soon. And we've already mentioned this differential privacy and this epsilon parameter earlier on for membership inference. Now, what you are seeing here in the right-hand side is, hang on, I need to move the zoom. Right, so this is the target image for a particular example. And these are the reconstructions we would get by running the attack according to various epsilons. So here, this means the most private setting. This is the least private setting. And you can see that for quite gigantic values of epsilons, the attacker still finds it hard to figure out the correct reconstruction. Now, if you have a terrific memory, because I should have pointed this out earlier on, but in the membership inference case, we dealt with epsilon equal to 4 or 10. They were already quite big numbers, and they were not, well, especially 10 was not really sufficient to protect against the attack. Here we have to deal, we are dealing with an epsilon equal to 10,000, and we're able to actually protect against these attacks. So this really goes to show that by choosing the threat that you care about in advance, you can actually get away with a much bigger privacy budget, as we'd call it. Mind you, of course, the bigger the epsilon, the better the utility of your model. So the bottom line is, if you only care about protecting, against reconstruction attacks, well, you can get a much more accurate model in the end, which is still secure. Cool. So I mentioned this a couple of times, and here we are. How do we ensure that a model is private? And the sort of state-of-the-art, or if you wish, the most mainstream way of ensuring that a machine learning model is private is by ensuring that it satisfies this particular definition that I have here. So this is called epsilon differential privacy. The idea is as follows. Say you have some algorithm, and then you run this algorithm on one set of data records, and then you run it again on the same set of data records plus one additional record. And ideally, you would like for the algorithm to satisfy privacy of the records. You would like the outputs to be similar. In some sense, you're asking that the contribution of the additional data record doesn't play much of an influence on the outputs of your algorithm. So for neural networks, say, this means that if we train two neural networks, one on some training set and the other one on the same training set plus 1 point, the two networks should look pretty much the same. So, and this is where we get this epsilon value, right? And smaller epsilons, of course, mean better privacy in some sense. Now, in practice, we actually tend to use an approximate version of this. It's called epsilon delta differential privacy. Kind of same definition. Now this time, so epsilon controls how much leakage we allow, but we are allowed to violate that leakage with probability D. I think this gives to be the best intuition of it. Cool. So what do we do with these definitions? Well, we're lucky because there's been 15 years, 20 years of research in the area, and we have algorithms that do satisfy differential privacy and that allow us to train neural networks. So that's pretty cool. What you're seeing here, this algorithm, this is just an extension of the standard stochastic gradient descent algorithm that you'd use for training your neural network. Only this time, it ensures differential privacy. Now, how the epsilon deltas are computed, we'll get to there in a second. But the idea is that this algorithm just ensures that each individual data record does not influence too much your learning task. Now, we have all these beautiful theory, and we know we can train neural networks that satisfy differential privacy. But there's various problems with that. The first one is, well, how do we actually interpret the values of epsilon delta? I'll show you an example. How do we measure them? Again, we'll see in a second. And even how do we compare between algorithms satisfying similar epsilon delta values? Now, the kind of spoiler for this is, in my very own opinion, that if you actually define the attacks that you're really concerned about, all these questions become quite easy to deal with. So how do we interpret epsilon delta and how do we act on them? So let me first clarify what I mean by acting on some values. Say you want to train a machine learning classifier based on customers' data or health data. But of course, thanks to GDPR, if you're in Europe, you should not be allowed to store data for more than a certain amount of time. And well, if you train a machine learning model that's actually memorized the data, that you know, you do wonder, am I doing the right thing? Am I being compliant? Now I'm going to tell you, well, look, your model satisfies epsilon equal 10 and delta equal 10 to the minus 6. Is it good? Is it going to comply? This is a very tough question. This is a very, very tough question, and I'm not going to aim. Well, I cannot promise to try and bridge kind of the math to the policy side. I'm not a lawyer. Don't take any sort of law advice from me. But what I can say is that these values, in my opinion, are meaningless on their own until you actually start considering the threat model. So if you do consider the threat model, say membership inference, epsilon equal to 10 means absolutely nothing. We can provably find an attack that achieves 100% success rate. And even empirically, well, empirically, we do see epsilon equal to 10 does offer some protection. This is a sort of limitation between formal and empirical, if you wish. But regardless, membership inference, epsilon equal to 10 is actually quite weak. But then if we go to the other end of the spectrum, so if we go to reconstruction attacks, well, we have seen that we can actually get away with a very, very big epsilon. And indeed, if your data is d-dimensional, you can get away with epsilon equal to d, probably, mathematically. And empirically, we can see the same. So yeah, how do we interpret these values? Pick the threat model you want, and that should help you figure it out. Now, the second problem I listed was, well, how do we measure epsilon and delta for DPSGD? So currently, there's very, very advanced algorithms that take in the parameters of DPSGD and estimate these epsilon delta values. But then a couple of years ago, we set out the question, well, what if we could compute the risk for a model against a specific threat, say membership inference, without having to pass by epsilon delta? And well, I mean, I would not be answering this question if I couldn't, I would not be asking this question if I couldn't answer it. Yes, we can actually do that. So this inequality here just shows that based on the parameters of the DPSGD, you can get a bound on the, let's say on the advantage of the attacker that we saw before. This is a very, very rough idea, but I'm also aware of time, and I wouldn't want Maura to get stressed out about this. So I think the best way to kind of show this inequality is to actually plot it, and we can get an interactive calculator that shows you how secure you will be with respect against membership inference attacks for your chosen DPSGD parameters. So you can pick your number of data records, your batch size, and then noise parameter, that's another parameter. Based on that, we get a value of security. We call this base security. Higher is better, 1 is perfect. And it can be related to various other notions, such as probability of success, advantage, and so on and so forth. There is something slightly even better that we can do. So this is just for membership inference. But something that's kind of annoying when you do theory is that theory is that you could be proving very weak security against something, but then in practice, things actually do much, much better. That tends to be the case. So what we did was, for the case of attribute inference, we were able to kind of instrument, if you wish, or modify DPSGD so that it captures more effectively the actual contribution of each data record and each attribute value, essentially. And this means we're making much, much weaker assumptions, if you wish, from the theoretical sense. And we get a notion of security or a measure of security that is much, much closer to what it is in reality. So plots speak much better than words. What you're seeing here is, well, the model accuracy and security. So we do know that by the constants in PPML, the more your model is accurate, the less secure it will be. This blue line shows your security against membership inference, and indeed it does degrade quite a bit. But then, if we actually run our attribute inference analysis as well as shown as per this algorithm, we actually see that we get a much better security. And this is quite an important result. I mean, it's quite a remarkable, I guess, difference. We can get a model that is, 0.7 accurate, 70% accurate, which for the particular data set was good enough, but still retain practically 100% security according to this notion. Whereas if we cared about membership inference, well, we might not be able to deploy the model at all. Cool. Well, yeah, this is the paper that we wrote on this topic. So I think, yes, I think I'm very close to concluding. So we looked at two of these three problems. We looked at how to interpret epsilon delta values and how to measure epsilon delta values. Now, it turns out that comparing epsilon delta values is very hard. There was a very, very nice work by Natasha Fernandez. I'm going to link it in my slides, which showed that if you take two algorithms that are equally epsilon delta secure, they could still exhibit different sort of resilience to attacks. So one could be weaker than the other one. And so my bottom line, as I mentioned, is, well, just define a threat model. If you define your threat model, then it should make all these questions much easier to answer. Cool. So I promised this would be a sort of tutorial or overview of privacy attacks against machine learning models. And I cannot omit one important aspect, and that is all the attacks we considered, membership and attribute inference and reconstruction attacks, they were all about one individual data record. But then it could be that we are interested, or the attacker rather, is interested in more data records. So say that we train a model based on user data, but each user contributes with more than one data point. Well, that surely must make the membership inference attack much easier, right? If the goal of the attacker in this case becomes did this particular user contribute to that data set, now they have, well, the model has seen many more data records about that particular user. So this is indeed a big risk, and it is not tackled directly by differential privacy. It can be, of course, but it led to this nice work, which actually dates almost 10 years ago. Wow. Where Frederickson et al. Showed that they could sort of leak information from a face verification system. So face verification system was a machine learning model trained on multiple data points belonging to a user. And based on that, they were able essentially to reconstruct what the user, or what the average data point looked like, and that is what the user looked like. So these are, again, many concerns that you need to consider. So kind of to recap, we looked at 3 attacks, I would say the most important attacks within the area of PPML. And by considering them, you will be getting, by doing an accurate threat model analysis, you will be gaining a lot of accuracy in your model, and you will get a much better understanding, essentially, of its security itself. We looked a bit at DPSGD. There's plenty of open problems, but hopefully I gave you an idea of what all these PPML is about, and yeah, and hopefully I left you with some questions. So I'll be happy to answer some of them here, of course. So thank you for listening.
So thank you so much, Giovanni, for the very, very amazing talk. So it's time for questions. We will start answering the ones from the Zoom call, and then we're gonna read also some that are like also on the YouTube chat. So feel free to raise your hand, and I'll give you like the power to ask questions. Don't be shy.
I have a question to break the ice if you want.
Yes, you go.
Yeah, thank you for the great talk, Giovanni. It's really very interesting, and you made it easy to understand, which is not always the case when, at least for my side, when looking at the privacy-related topics. I wanted to know, because this is a problem on the evasion attacks and the adversarial machine learning field in general. I wanted to know to what extent this research is done on images, And if there are other cases, other kind of data, other domains that appear, you showed one case in your challenge, but I wanted to know if this is a general thing in the literature or it's only one outlier.
So yeah, that's a very good question, and I mean the fun answer should be images are much easier to capture in slides, and they give a much better idea, especially I guess for reconstruction attacks, where to answer your question, these attacks do tend to be applied. I mean it's quite a broad spectrum. So in terms of attacks, you can have tabular data, plenty of it, especially as you could imagine for attribute inference. Images, of course, but also text. Of course, nowadays there's a huge amount of research on leakage of large language models and so on. We should say that I should say perhaps that in terms of defenses, we understand very well how to protect tabular data, how to protect, say, images to a good extent. For language, we can apply DPSGT, but the actual implications are can be a bit more subtle than that. So say that you care about private information, so within a portion of text. Now that becomes a bit more challenging, at least from the formal side. But yeah, I would say a bit of all of them. Yeah.
Yeah, indeed. I think it's difficult to understand. You know, if you study very well the problem in images, for instance, then what happens if you have other data? Because this is what's going to happen. For instance, in all the companies that want to use machine learning, not necessarily they work with images. So, yeah, it's an open problem for sure.
Yeah, very true, very true. Yeah.
Thank you for the question and answer. I think we have time for like a couple of more questions. Again, raise your hand or type. Also, if you want to type the question in the chat, I can read them loud. So I guess everybody was satisfied with the talk. So I think that Mauro, I think that we can go to the closure of this event.
Actually, I will go with another question
Let's
because
go
I
for
like
it.
the topic. So my question is, what about models that are fine-tuned? So if I have a model and I start from a pre-trained model, actually, and I fine-tune it on a subset of data, does this affect privacy and to what extent?
Yeah, that's again a very good question, and indeed one pattern I'm seeing, I guess even at company level, is that I mean it is it can be very easy, say, to train a model based on public data, or start with a pre-trained one, right? And then just do the last fine-tuning part on private stuff. So if you do want to satisfy privacy, if you do want your final model to be private with respect to the fine-tuning data, then you should use DPSGD or one of the alternatives. There's no escaping that. The good thing is that you can actually do fine-tuning with DPSGD. Yeah. If you care about the privacy of the original data set, I cannot think of many scenarios where that might happen.
No, sorry. I was thinking more of, maybe the attacker has more knowledge than we expect. If they know, for instance, that the model is pre-trained on ImageNet, they know already something about the model. So they only need to understand the delta, let's say, from the starting point. I don't know if that makes sense.
Yeah, no, that's a very, very good point. It might be possible to exploit that a bit further, for sure. Yeah, no, it's a very nice point. Yeah.
Like there are some like underlying vulnerability, like privacy vulnerability on the model that you use for pre-training, let's say.
Yeah, mostly
Okay.
it's still some leakage if you know that a model is pre-trained,
Yeah.
and maybe you know that the model already reacts to some inputs, and then you can, understand more of the change from the original model to the later. Yeah, but it was a complicated question, so probably the answer is
yeah. I mean, the answer might be a research project.
Yes,
but no, but I think it makes a lot of sense, especially when we talk about practical attacks, right? I mean, plenty of research, and I'm guilty of it myself, as I showed, does work on, or has been working on, kind of less than realistic scenarios, right? So the Miko challenge that we launched, we did want to get a benchmark, right, as realistic as possible, but still, I feel like we like in the real world, these attacks could be even harder to perform, and so ideas such as yours to exploit knowledge of the model before fine-tuning might actually give a very, very big advantage. Yeah.
right. So I think that was the last question, unless somebody has one last minute question, but no, I don't see raised hands. So thank you again, Giovanni, for the great talk and also for answering my questions. And thanks all for joining. So see you next time.
Yeah, thank you.
Okay, so streaming terminated now.